Good morning, everyone. So welcome to my YouTube channel, Math Sutram. So today we are going to see 8th lecture on Riemann integration. Okay. So let's start today's session now. We are denoting RAB means collection of all the Riemann integrable function over AB. F close interval AB to R such that F is Riemann integrable. Okay. So today we are going to see this theorem. Let's say theorem 1. Let F interval AB to R be a bounded function. Okay. Then F belongs to RAB. It means F is Riemann integrable if and only if given any epsilon greater than 0, there exists delta greater than 0 such that UPF minus LPF is less than epsilon for all P partition of AB with their norm less than delta. Okay. So let's see its proof. First, assume that given any epsilon greater than 0, there exists delta greater than 0 such that UPF minus LPF is less than epsilon for all P partitions of AB with norm P less than delta. Oh, we know that LPF is less than equal to lower integral and lower integral is less than equal to upper integral. Okay. So what does it mean? It means the distance between these two will be less than equal to distance between UPF minus LPF. So this implies A to B fx dx minus A to B fx dx lower integral is less than equal to UPF minus LPF. Let epsilon greater than 0 such that UPF minus LPF okay. Then what we have? We have this one. So A to B fx dx minus A to B fx dx is less than UPF minus LP. This is less than epsilon. So this also will be less than epsilon. So this implies A to B fx dx A to B lower integral is less than epsilon. But epsilon greater than 0 is arbitrary. Okay. And this is because upper integral is always greater than lower integral, and this quantity negative, non-negative also. So what does it mean? It means this quantity has to be 0. So this implies because epsilon greater than 0 is arbitrary. You can make as small you can. So it means this quantity is 0. So this implies A to B upper integral is equal to lower integral. Okay. So what does it mean? Then lower integral is equal to upper integral. What does it mean? It means that f is Riemann integrable. So this implies f belongs to RAB. Okay. It means f is Riemann integrable. Okay. Now conversely, assume that f belongs to RAB. Okay. Let epsilon greater than 0 by Darboux theorem. Darboux theorem, we have by Darboux theorem, there exists delta greater than 0 such that UPF is less than upper integral and LPF is greater than lower integral for any partition P with any partition P of AB with norm of P less than delta. Okay. Since F is Riemann integrable, we have A to B fx dx is equal to A to B upper integral is equal to lower integral, because function is Riemann integrable. So that what we have? We have UPF that was less than upper integral, but now this is nothing but, what is this? This integral is A to B, because function is Riemann integrable. Okay. So this implies UPF is strictly less than A to B fx dx plus h by 2. Let's say this is equation number 1. Okay. And LPF, okay, LPF is greater than A to B lower integral minus epsilon by 2. Now this is equal to A to B fx dx minus epsilon by 2. Okay. Now how we can write it? Multiply both the side by minus, so the inequality will change. Okay. So this is for any partition B of AB with norm of P less than delta. Okay. And this is also for any partition P of AB with norm of P less than delta. Okay. So from 1 and 2, we have UPF minus LPF. So UPF is less than A to B fx dx plus epsilon by 2. And what is L? This is minus A to B fx dx plus epsilon by 2. So this cancel out. Okay. So what is this? This is epsilon by 2 plus epsilon by 2. That is epsilon. So this implies UPF minus LPF less than epsilon for any partition P of AB with norm of P less than delta. So this theorem is proved. Okay, we have proved this theorem. Okay, this theorem is proved now. Now we'll write a corollary. Corollary means it is a small result which comes by theorem. Okay, which immediately follow by the main result. We have proved the theorem and we are going to write a small result. Okay, let f close interval AB to R be a bounded function. Okay. Then f belongs to R A B if and only if limit norm of P tends to 0 UPF minus LPF, this limit is going to be 0. Okay, let's see this proof. So first assume that limit UPF minus LPF is 0. So what does it mean? It means given any epsilon greater than 0, there exists delta greater than 0 such that the meaning of this is this: given any epsilon greater than 0, there exists delta greater than 0 such that UPF minus LPF is less than epsilon for any partition P of AB with norm of P less than delta. But by theorem, what is the meaning of this? This is necessary and sufficient condition, because in theorem we have studied if and only if statement. Okay, that is some part of that theorem, one directional part. Okay, so by the theorem 1, we have f belongs to RAB. It means f is Riemann integrable function. Okay. Now, conversely, assume that f belongs to RAB. Okay. By theorem 1, given any epsilon greater than 0, there exists delta greater than 0 such that UPF minus LPF is less than epsilon for any partition P of AB with norm of P less than 10. Okay. So what is the meaning of this? What is the meaning of this? The meaning of this is limit norm P tending to 0, UPF minus LPF is actually 0. So this corollary is proved. Okay. So this corollary is proved. Now we are going to prove another theorem. Let's say it's theorem 2. Let F close interval AB to R be a bounded function. Then F belongs to RAB. It means F is Riemann integrable if and only if there exists P partition of closed interval AB such that UPF minus LPF is less than epsilon. Okay. Proof. First, assume that for any epsilon greater than 0, there exists P partition of closed interval AB such that UPF minus LPF is less than epsilon. Okay. Okay. But we know that LPF is less than equal to lower integral FXDF and lower integral is always less than equal to upper integral. And upper integral is always less than UPF. Okay. So what does it mean? It means the distance of UPF and LPF is always greater than the distance of upper integral from lower integral. Okay. And this is less than epsilon. And this is because upper integral is always greater. So this will be also less than epsilon. So this implies for any epsilon greater than 0. Okay. Or okay. Since epsilon greater than 0 is arbitrary, we can choose it as small we get this quantity has to be 0. So this implies A to B So what does it mean? It means lower integral is equal to upper integral. What does it mean? Then both the integrals are equal, function is Riemann integral. So we have this one. Okay. Conversely, assume that f belongs to R A B. Okay. Since f belongs to R A B, we have, because f is Riemann integrable. If f is Riemann integrable, what we have? Upper integral will be equal to lower integral. It means a to b fx dx. Upper integral is this, because function is Riemann integrable. So upper integral and lower integral both are equal, and we are calling this integral a to b fx dx. This is called Riemann integrable. Once a function is Riemann integrable, the common value is called Riemann integral of f. Okay, over a b. Okay. Let epsilon greater than 0, because UPF is what? UPF is what is the upper integral? What is the upper integral? How upper integral is defined? A to B upper integral is defined as the infimum of UPF, where P is a partition of closed interval AB. Okay. Now, if you will add something in infimum, there will be partition. So this implies there exists P1 partition of AB such that, because we are adding something in infimum, let's say epsilon by 2, this is this is positive quantity. So there will be always a member here. So UP1F satisfies this. So once a one partition will be there, which will be strictly less than UP1F will be strictly less than. Let's say this equation number 3. Okay. And what is LPF? What is LPF? LPF is supremum of, this is lower integral. I want to write here lower integral. Somehow it is being mistaken. A to B lower integral is supremum of LPF. P is a partition of closed interval AB. Okay. So if I will add, if I will subtract something from supremum, okay. If I will subtract something from supremum, so this is the supremum. So I am subtracting something from here. Let's say epsilon by 2. So there will be, implies there exists a partition. There exists a partition P2 of AB such that some LP2F will be greater, because we are subtracting something positive quantity from supremum. So Now this quantity is no more a supremum. So there will be some P2 of closed integrability partition such that this will happen. That's it. This equation 4. Okay. Okay. But here, so in the equation number 3, you observe one thing. But function is Riemann integrable. So this lower integral is equal to what this is? This is equal to a to b fx dx plus epsilon by 2. So what does it mean? It means that UPF is less than a to b fx dx plus epsilon by 2. Now say it equation number 6. Okay. Same here. You write here the value of this because function is Riemann integrable. So this is equal to so it is implies LP to F is greater than A to B Fx dx minus epsilon by 2. This is equation number 4. Okay. So put P is equal to P1 union P2. Then P1 is contained in P. So this implies UPF is less than UP1F. Okay. And P2 is also contained in P. So this implies LP2F is less than LPF. Okay. But LPF is always less than UPF. Okay. So this implies now LPF is less than UPF always. But this is less than UP1F. Okay. And this is less than LP1F. Sorry, P2F. Okay. But this is strictly less than A to B Fx dx minus epsilon by 2. Okay. But this is less than A to B Fx dx minus epsilon by 2. Strictly less than. Okay. From equation 3 and 4. Okay. So now what we have actually? So we have A to B Fx dx minus epsilon by 2. that is still less than u, that is still less than LPF. So let's say in bracket, and this is less than UPF, and then it's less than A to B after KX plus epsilon by 2. Here it is epsilon plus by 2, F plus. Okay. Now what is the distance between these two will be less than distance between these two. Okay. So this implies UPF minus LPF is less than, is strictly less than A to B after 3x plus epsilon by 2 minus A to B after dx minus epsilon by 2. So what is this? Just open minus sign and bracket. This is epsilon by 2. So this is cancelled. So this implies epsilon by 2 plus epsilon by 2. So this implies UPF minus LPF is less than epsilon. Therefore, there exists the partition of closed interval AB such that UPF minus LPF is less than. So theorem is proved. Okay. So thank you very much for today's lecture. If you have any problem related to this, you can comment on my YouTube channel. We will see you next lecture. Thank you very much. Like, share, comment and subscribe my YouTube channel.